Hi everyone, this is Babaiah, Assistant Professor of ECE Department, MLR Hyderabad. Today I am going to derive some or solve some problems based on the time domain specifications as well as steady state error. In previous session we learned how to derive the steady state errors for the various inputs as well as time domain specifications. All these are learned from the previous session, but today now I am going to derive some or solve some problems based on the steady state error as well as the time domain specification. Now move on to the first here. The first problem, for a servo mechanism with one with a open loop transfer function given below, and explain what type of input signal gives the rise to a constant steady state error and calculate their values. Here just simply in open loop transfer function, here these are given the open loop transfer functions which are gives to which type and which type of input signal and which steady state error is the calculation and what are that steady state error value and type number of the system. The two are going to be calculated by giving the open loop transfer function. See here, the first open loop transfer function g of s equals 20 into s plus 2 divided by s into s plus 1 s plus 3. So let us assume unity feedback system, that is h of s is equals to 1 here. So we know that unity feedback is h of s is 1. We consider here the open loop system has pole at origin. The first one, see, observe here one pole present at origin, right? See, one pole present at origin means the single pole at s equals to 0, that is nothing but the pole in denominator part. S terms is nothing but the poles. So one pole present at the origin, right? So this is the type 1 system. From this, that is the type 1 system. And also one more here in this question, what is the constant steady state errors also, right? So here see, in this system the type number is type number 1. So the velocity type number 1 means here ramp signal is the input signal, right? So ramp signal is the input signal, that is the velocity or ramp input gives a constant steady state error simply for type 1 system. So here the steady state error with unity velocity input, that is ESS equals to 1 by kV. The velocity error constant kV equals to limit s tends to 0 s into g of s into h of s. This is, we know that formula for velocity error constant, right? In previous class also you can refer that. Kv equals to limit s tends to 0 s into g of s into h of s, right? Here substitute s equals to 0 for that, and h of s is equals to 1, right? So unity feedback, so here h of s equals to 1. So let s tends to 0 s into g of s. So here already in g of s given question is g of s is there, just to substitute here limit s tends to 0 s in place of g of s 20 into s plus 2 divided by s into s plus 1 s plus 3, that is equals to 20 into 2 divided by 1 into 3, that is 40 by 3. So 40 by 3, that is steady state error. Steady state error is nothing but ESS equals to 1 by kV, right? Steady state error equals to 1 by kV. So 1 by kV means here kV is the velocity error constant, that value is 40 by 3. Just to substitute 3 in place of kV, you will get the 0.075. This is the first bit, right? Next, coming to the second question, second bit here. This is a given open loop transfer function g of s equals to 10 divided by s plus 2 s plus 3, and here let us assume same as unity feedback system is 1 and the open loop system has no pole at origin. Here in observe denominator part there is a no pole present at origin, so that's why the type number is 0. Simply we say that type number is 0 system. In systems with the type number 0, the step input will give a constant steady state error. Constant steady state error. The steady state error with the unit step input, that is steady state error equals to ESS equals to 1 by 1 plus Kp for the unit step input. Here type 0 system, right? Type 0 system means the input signal is what? Step input or unit step. right? Step input signal or unit step input. Type 1 is a ramp signal, right? So for ESS 1 by 1 plus Kp, Kp is the positional error constant, that is Kp equals to, we know that formula, limit s tends to 0, g of s into h of s, that is equals to h of s equals to 1. So g of s is given in from the problem. Just to substitute here, s equals to 0. 10 divided by s plus 2. So 0 plus 2, 0 plus 3. So 10 divided by 2 into 3, 5 by 3, right? So steady state error ESS equals to 1 by 1 plus Kp for the unit step input. So 1 by 1 plus Kp in place of 5 by 3. So by solving, you will get the 0.375. Okay. Next, coming to the third bit, g of s equals to 10 divided by s square into s plus 1, s plus 2. Let us assume unity feedback system, that is equals to h of s equals to 1, right? The open loop system has two poles. See, observe. In denominator, s square term is there. That is the poles presented. So poles, how many poles? Square. So two poles present at origin. So the type number is 2. Type number is 2. That is the input signal is what? Parabolic signal or acceleration. Acceleration input or parabolic input will gives the constant steady state error. Already we know that steady state error with unit acceleration input, that is ESS equals to 1 divided by Ka. Acceleration error constant Ka equals to limit s tends to 0, s square into g of s into h of s. Limit s tends to 0, s square into g of s, h of s equals to 1. So s square into g of s, limit s tends to 0, s square, g of s equals to that value, just to substitute, you will get the 5. So this is the 5, that is acceleration error constant. But we know the steady state error for the acceleration input. So steady state error for acceleration, ESS equals to 1 by kv, right? 1 by ka, sorry, 1 by ka. So ka equals to acceleration error, that is equals to 5, right? 1 by 5, that is equals to 0.2, right? These 3 bits. Okay. Next, coming to the second problem, see how the response. This second question is just the response of servo mechanism is c of t equals to 1 plus 0.2 into e power of minus 6t minus 1.2 e power of minus 10t when subject to unit step input. Here, input signal is unit step. Obtain an expression for closed loop transfer function. Determine the undamped natural frequency and damping ratio. Here undamped natural frequency, that is nothing but omega n, and one more damping ratio, that is the zeta. We need to calculate these two. Okay. So here the given equation or given time response, c of t equals to 1 plus 0.2 into e power of minus 6t minus 1.2 into e power of minus 10t. And taking Laplace transform are both sides, c of t, you get c of t, Laplace of c of t, c of s. So 1 of Laplace of 1 by s, 0.2, 0.2. And e power of minus 60, Laplace of e power of minus theta or minus a theta, e power of minus a theta Laplace, that is equals to what? 1 by 1 plus a, this value a. So here a equals to 60. So 60, 1 by s plus 60 minus 12 into same this formula only, e power of minus Laplace of e power of minus a t, that is equals to 1 by 1 plus, sorry, 1 by s plus a. So here 1.2 into 1 by s plus 10. By solving this one, just s into s plus 60, s plus 10. Okay, LCM. Here one term s is there, these two are just in numerator, plus 0.2 into these two are multiplied here, minus 1.2 multiplied with these two, right? Okay, by solving, s square plus 70s plus 600 plus 0.2 s square plus 2s minus 1.2 s square minus 72 s divided by s into s plus 60 s plus 10, that is equals to 600 divided by s into s plus 60 s plus 10, that is equals to 1 by s into 600 divided by s plus 60 s plus 10, s plus 60 s plus 10. Since input is unit step, r of s equals to 1 by s. So input unit step, right? So Laplace of input signal r of t is nothing but r of s. So r of s equals to 1 by s. 1 equals to 1 by s. Here r of t input signal, that is equals to 1. So Laplace of 1 is equal to 1 by s, r of t, r of s. So substitute in r of s, 1 by s, substitute. Okay, c of s equals to r of s. Here c, observe, 600 divided by s into s plus 60 s plus 10, 1 by s is common. So 1 by s is nothing but the r of s. So r of s into 60 divided by this value. This is the then c of s divided by r of s. Finally, c of s divided by r of s is the transfer function, right? In question they are asking closed loop transfer function, that is equals to 600 divided by s square plus 70s plus 600. From that we are going to calculate these two values, nothing but undamped natural frequency as well as the damping ratio. We know that formula. The damping ratio and the natural frequency oscillation can be estimated by comparing the system transfer function with the standard form of second order transfer function. Just comparison of the standard form of second order transfer function, that is c of s divided by r of s equals to omega n square divided by s square plus 2 zeta omega n s plus omega n square, that is equals to 600 divided by s square plus 70s plus 600. On comparing we get omega n square equals to 600, omega n equals to under root 600, 24.49 radians per second. So this is the 2 zeta omega n equals to 70, zeta equals to 70 by 2 omega n, 70 divided by 2 into 24.49, that is 1.43, right? This is the zeta value, damping ratio and natural frequency oscillations, right? These two are the problems. Next, coming to that third problem, see here, a unity feedback control system has an open loop transfer function g of s equals to 10 divided by s into s plus 2. Find the rise time, percentage overshoot, peak time, setting time for a step input of 12 units, right? The unity feedback system is shown in figure. The closed loop transfer function c of s divided by r of s, that is equals to g of s divided by 1 plus g of s into h of s, where h of s equals to 1. So closed loop transfer function given g of s equals to 10 divided by s into s plus 2. So just this is the input signal r of s, output is c of s, rest input and output c of s, g of s is the gain, open loop gain. So feedback, this one, feedback h of s equals to 1. So unity feedback, right? So here c of s divided by r of s, that is equals to 10 divided by this value. Already here g of s is there, so substitute g of s value divided by 1 plus g of s from 10 divided by s into s plus 2 plus 10 by s square plus 2s plus 10. Okay, the values of damping ratio zeta and the natural frequency of oscillation omega n are obtained by comparing the system transfer function with the standard form of second order transfer function. From this transfer function compared with the standard form of second order transfer function, that is here. So second order transfer function is here. Already we know that this one, just to see, zeta standard form of second order function, c of s divided by r of s, that is equals to omega n square divided by omega n square Just to see, omega n square divided by s square plus 2 zeta omega n into s plus omega n square, right? And comparing the equation 1 and 2, this one is the equation 1 for example, and compare with the second order transfer function. So here observe omega n square, that is equals to 10. 2 zeta omega n, this 2 zeta omega n is equals to, just compare here, 2 zeta omega n is 2 only, so 2. So from this omega n equals to under root of 10, that is 3.162 radians per second, and also 2 zeta omega n equals to 2, so zeta equals to 2 divided by 2 omega n, so value is 0.316. So we know that theta equals to tan inverse of 1 minus zeta square under root divided by zeta. This is the theta value, angle calculation. So just to substitute the zeta value in place of zeta, you will get the 1.249 radians theta angle is. Then omega d, damped frequency oscillations. Omega d equals to omega n into under root 1 minus zeta square. Substitute the omega n value and zeta value, you will get the damping frequency 3 radians per second. Next, we need to calculate what are the calculation from here. Question, just observe question there. See, rise time. So rise time calculation, percentage overshoot and percentage overshoot or maximum peak overshoot or peak time and settling time. All these four we are going to calculate for 12 units. So here see, percentage rise time, first tr equals to t suffix r, rise time 5 minus theta divided by omega d, just to substitute you will get the 0.63 seconds. And percentage overshoot, maximum peak overshoot, percentage of peak overshoot, e power of minus zeta 5 divided by 1 minus zeta square under root into 100, that is equals to percentage. So you substitute, you will get the value 35.12 percentage. Next, see, peak overshoot. We know that here this is the peak overshoot, right? 35.12, but from the problem 12 units are available, so 12 units of peaks, so divided 35.12, see here 35 percentage, so 35.12, so 35.12 divided by 100 into 12 units, you will get the 4.2144 units. Next, peak time, TP equals to 5 by omega d. Omega d we know that 5 by 3 equals to 1.047 seconds. Next, time constant, t suffix s. Settling time, for t calculation of settling time ts equals to what, 3t for the 5 percentage, for the 2 percentage what, settling time 4t. So where t is nothing but what, time constant, this one. So time constant, for time constant the formula t equals to what, 1 by zeta omega n. Just substitute the zeta value and omega n value, you will get the time constant, so that is 1 second. For 5 percentage error, settling time equals to ts equals to 3t, 3 into t is equals to 1 second, so 3 seconds. For 2 percentage error, settling time ts equals to 4t, 4 into 1 second, that is the 4 seconds, right? All this time constant, settling time, peak time and peak overshoot and rise time and maximum peak overshoot, all these are calculated. So these are the problems about the from the time domain specifications and steady state errors. This is about the today's class, and also we have a more number of problems are there, but there is a few time is there, we will continue the next class, or else you can same thing, you need to follow the, or else remember all these problems, formulas, very important. So from the next class I am going to start the next to topic. So here these are the basic problems. So we need to solve these problems like by using the formulas. The formulas are very important for the gate level also. For that you should remember all this: rise time, peak time, and percentage overshoot, settling time, and also damped frequency oscillations, velocity constant, positional error constant. All these formulas are very important for the gate level. And this is about the how to solve the problems by using the time domain specifications and steady state errors. I hope you all understood all these problems how to solve, and thank you all.